technical information background. I'd like to introduce to you Adib Abdelkader, the project manager on this piece of equipment from corporate engineering. He'll be controlling the meeting. So, Adib. I'd like to begin this meeting by thanking all of you for taking the time from your busy schedule to attend this meeting. Since the program was approved on preliminary information, I have asked key members from the project group to come to Des Moines and update you on their respective area and to answer any concern you may have at this point. At this point, I would like to have everyone in this room introduce himself and the area of his responsibilities. If we could begin with Mr. Leo.
Randros, I'm with the project engineering, and I work for Mr. Schaefer.
Jim Tveekrem, I'm with Firestone Central Research. Worked in radiation area for years now.
Walt Tarashuk, I'm with Automation Controls, and I'll be following the electrical services.
Ed Curley, I'm Systems Engineering. I'll be working with the lining equipment. Al Daigle and Passenger and Light Truck Processing Engineering. Reviewing some of the historical data we have and tests we've had on this Electron Beam precure. Optimize, hopefully, when the system cuts downstream in Wilson, we'll try to optimize the conditions, the processing and whatnot.
I'm Ed Seeley, passenger light truck materials compounding, particularly body ply skims. And I'll be updating you on the test that we currently have running on the pre-cured body ply passenger tires.
I'm Chuck Allen, heavy duty truck and rear tractor tire processing, Akron. I'll be reviewing with you the process information we have and the status of our tests on tractor tires and truck tires.
Bill Gibbs, staff engineer here at the plant.
Dave Dirk, section manager of plant engineering here at Des Moines.
Wes Jones from Hamilton. I'm the project manager in the engineering department.
Mike Flannery, I'm with Shy Battery Engineers, the consulting firm, helping Jim on the general trades and demolition thing.
Jim Schaefer, construction manager on the project.
Al Wall, quality control.
Hey, Cal Newton, foreman of calendars. I'm the guy that's going to have to run this once you get it installed.
Charlie Green, QA manager, plant.
I'm Jim Allpress, run the quality circle from Des Moines.
Elvin Hone, for this project I'm in environmental engineering. Gene Ricker, industrial engineering.
Dick Hubbard, industrial engineering. Russ Littby, plant engineer.
Art Ager, industrial engineer.
Okay, thank you. The meeting tentative agenda is that Dr. Tveekrem will begin part of the presentation reviewing theories of operation and usage of electron beam systems. Then Chuck Allen will review tests and results of tests made on pre-cure material on heavy-duty tires. And then Al Daigle will review the history of tests and results we've done on electron beam and also on pre-cure material. Then Ed Seeley will review tests and results of pre-cured material on passenger and light truck tires. Ed Curley will review Wilson line arrangement and the operation. Walt Tarachuk will answer any question in regard to system controls or power requirements. We have Mr. Jim Clement from Radiation Dynamics, who will join us this late this morning or early afternoon. He will review radiation dynamic equipment operation and safety. In regard to the project schedule, we have established a preliminary schedule and also a more detailed one, which is the critical path method, and they are preliminary. I will leave them with Jim Schaefer, so the plant will have the input in regard so before we issue a final one. In order to save time, I just point out to some key milestones. The demolition work, preparing the building where the electron beam system is going to be installed already is underway. Jim is working with the local consulting engineer to do that. We expect the building modification to be complete, hopefully, by the first week of December this year, 1984, and the vault to be installed by the end of February 1985. We are shooting to issue a contract for Radiation Dynamic Incorporated for the equipment by June 30. The reason because they gave us a quotation, and it is valid until that point. Otherwise, we may have to pay about, I think, $30,000 premium on each system. We are also projecting to begin installation for RDI equipment the week of June 3rd, 1985. Line equipment installation, which consists of compensators, shuttle let-off and wind-up, to begin the first week of August 1985. Our projected checkout for the system to begin the first week of December 1985 with release to production February 10, the week of February 10, 1986. For the past month, we have been collecting data, and we put it into a project book, which I leave with Jim Schaefer and with engineering. The project book is consisted of different sections, such as the project description, assumptions made, justification, financial data, organization structure, and so on. The book will give the reader information in regard to the project and what the project is all about. The project book will be updated. New information will be sent to the plant to be inserted into the front of its section, so it will be kept updated. I want to say, please feel free to ask any question at any point when each member of the project team will make his presentation, because the whole purpose of this meeting is really to update you and answer any concern. Thank you again, and Dr. Tveekrem could begin his part of the presentation.
Thank you. There are handouts here which can be passed around covering this talk, and there are some for the other talks as well. Someone could click on that projector there, perhaps. I'd like to summarize here what I'm going to talk about this morning. First, I'll deal a little bit with the actual generation of high-energy electrons. Just in a very cursory manner, the gentleman from RDI will go into more detail on this later in the day. Then I will dwell a bit on methods of measuring the radiation dose that's actually deposited in your material that's being irradiated, and the various conventions and techniques that are used. Then we'll deal a bit with the distribution of the deposition of dose in the sample as a function of the thickness of the material, and how this relates also to the material handling configurations for the product. Finally, we will talk about the interaction of electrons with rubber and similar materials, and the various processes that go on, the generation of heat, the various cross-linking, yields that are anticipated for various rubbers, and some of the inhibitors and promoters that we are aware of that can be used either beneficially or non-beneficially in these processes. An electron generator basically is not much different than your ordinary TV set or a cathode ray oscilloscope, whatever you wish to call it. Basically, you generate electrons by boiling them out of a filament by heating the filament. These electrons then are accelerated by a high voltage that's applied to a tube under vacuum, and this attracts the electrons. They are accelerated to a particular kinetic energy, and then drift in a vacuum to some point where they hit something. In the case of a TV set, they hit a phosphor on your TV screen and cause blips of light, which you then see. In our case, they hit a thin titanium window and penetrate this window and then impinge upon a product. We have the filament where the electrons are generated, a tube under vacuum. The voltage is, of course, in this case, much higher than what we're thinking of in any TV sets or so. The machines that we're talking about for the plants will have a maximum voltage of 800 kilovolts. The range of voltage, for practical purposes, will be from 400 to 800 kilovolts. The beam current will range from 0 to 100 milliamps. This determines the rate at which you can deposit dose in your sample. The higher the current, the higher the dose you can deposit, and therefore the faster you can move your product through the facility. The electrons, after being accelerated, pass through a magnet which sweeps them in essentially a one-dimensional raster across the length of the window. You basically have a spot of electrons about an inch wide or an inch in diameter, and this is swept at 100 and 200 hertz back and forth across this window, and essentially then you have a curtain of electrons, if you wish, that pass through the window and hinge upon the product. And you can control the width of this scan depending on the width of the product. Essentially, you would set it to basically be just slightly wider, perhaps, than your product, so that you don't you want many of the electrons as possible, of course, to hinge on the product and not get constrained and material to be wasted. The one thing that people always worry about is whether there's permanent radiation developed with this, and the answer is no. The energy we're dealing with here is not high enough to cause any nuclear reactions to take place, so there is no radioactivity formed in any of the materials. You must have much higher energies for any nuclear reactions to take place. So this is just like any general X-ray machine. You turn it on and you have the radiation, you turn it off and it's gone. It's completely safe when it's turned off. As I said, the beam current controls the amount of dose which is deposited in the sample. The beam voltage, on the other hand, determines the penetration of the materials. Electrons have very low penetration on a comparative basis with, say, X-rays. In our case, with 800 kilovolt electrons, the total penetration will only be slightly over around an eighth of an inch of material. However, whenever these electrons interact with any sort of matter, they produce a large number of X-rays, and the X-rays can range in energy from the maximum energy of the electrons on down. These X-rays, of course, are very penetrating, and they are the things that we worry about in protecting personnel. We must shield these facilities to protect against the X-rays, and I've illustrated here the thickness of concrete or lead that's required as a function of the energy of the electrons. As you see, we'll be dealing here in the range of about 400 to 800 kilovolts. And in that range, you will have roughly from 3 feet to somewhere on the order of 4, a little over 4 feet perhaps of concrete to effectively shield personnel. If you use lead, of course, you would be dealing with somewhere in the order of a little over an inch up to perhaps 5 inches of lead. The problem with using lead is it becomes prohibitively expensive compared to concrete when you get over thickness of an inch or two. So normally concrete is used for these facilities. Well, then let's talk somewhat about how we determine the dose and just what the dose is defined as for these for electron radiation. The dose is the amount of energy deposited in 1 gram of material. Doesn't say anything about what's done with this energy, it's just the amount of energy you produce in 1 gram of material. The rad is the unit that has been used to measure the dose for many years. It's defined as 100 ergs per gram. A new unit called the gray has been in use for about 10 years now. It's the SI unit and is defined as 100 rads. This unit has some use for the areas of low dose usage, such as food irradiation, perhaps, where they're dealing with rather low doses. However, in rubber, we are concerned with much higher doses, generally in the range of megarads. And a megarad is 10 to the 6 rads, or also 10 joules per gram. And maybe in more familiar units, this is equivalent to 1.26 watt-hours per pound. Most of the processes that are economically feasible using this will be in the range of less than 10 megarads. And for most of our rubber processes, we're talking more in the range of 5 megarads for our radiation doses. It's convenient to have a simple equation to estimate how much dose you're going to deposit in your sample. And this is such an equation, which is based entirely on machine parameters that you can set, or the operator can set on the machine. R here would be the surface dose of your material in megarads. I is the beam current in milliamps, which is entirely controllable. F would be the fudge factor you throw in there. It's a fraction of the beam intercepted by the product. It's a geometric factor. If your beam is much wider than the product, you have to allow for that. But generally, for efficient use, you'd be operating somewhere 0.9 to 0.95, I would guess, for this factor. The area throughput of your product is the other parameter. And the dose, of course, is directly proportional to the amount of beam current, but inversely proportional then to the area throughput. Area throughput being defined as strictly as the line speed times the width of the product for a flat sheet-like product. Then we have a proportionality constant, depending on units that you use for these other parameters. In this case, would be 180 megarad units per inch feet milliamps. This, in terms of the machines that we're anticipating for the plants then, which are 800 kilovolt machines capable of 100 milliamps, assuming we were running them flat out, there would be 2 machines. You would have 200 milliamps of beam current. And assuming a product width of 57 inches calendar width, or 60 inches for rounding off purposes, and a line speed of 60 yards per minute. The maximum dose one could obtain on the surface of your product would be about 3 1/3 megarads under those conditions, maximum power on these 2 machines. In order to measure the dose deposited, then, which is particularly useful when you're setting up these processes, and then at later times useful as checking to make sure that nothing is wrong and that you're still receiving the amount of energy in your product that you are initially set up for. Some method must be available. Now, there are primary methods which will measure these on an absolute basis. However, they're not convenient for everyday use. These are calorimetry, where basically carbon or water is the material that's been historically used. You deposit all of the electrons in a piece of carbon or a container full of water and measure the heat rise as a function of the time or the current that's passed. And this is an absolute method. You essentially determining all of the energy that's put in by the amount of heat that's generated, since no other reaction can take place in these. You would only have heat generated. Another technique is to use an ionization chamber, which is a chamber which is filled with some easily ionizable gas. You pass the beam through this, ions are formed. You have a couple of electrodes so that you can attract all these ions, measure the current generated by the ions attracted to the electrodes, and then in this way determine the total amount of ions that were formed in the passage of the beam. However, for practical purposes, we are always dealing with secondary dosimeters. These must always relate back to some primary measurement by some form of calibration. The global standards or some other organization of this type will provide you with information along this line. And these generally, the practical ones, are plastic films impregnated with some type of dye which will react to the electron beam. Historically, in Firestone, we've been using blue cellophane, which is basically just that. Cellophane that had a blue dye impregnated in it. It was available commercially. It was cheap. It came in various widths and was very thin on the border or so, and very convenient to use. As you see, I'm using the past tense. They've stopped manufacturing it now, so we can't use that anymore. But we still have some supply of it, so we do use it around our research facilities at least. It was a blue color. It changed to a very pale blue as the radiation dose increased. This was measured spectrophotometrically, and with the simple calibration curve, the dose would be determined. The best similar product at the moment now is made by a company called Far West Technology in California. It's a nylon substrate, again with a radiochromic dye impregnated in it, which changes color on radiation dose. And the color change is again measured spectrophotometrically. This is what we'll be using in our Wilson plant, and I presume in the other plants as well. They sell a reader for those that reasonably inexpensive. You have to buy this reader, which is $1,000 or so, and then the films themselves are rather inexpensive. The advantages of these films, of course, first is they're cheap, they're easy to use, they're easy to handle, physically thin. If you wish to look, for instance, at the effect of the variation of dose as a function of the thickness of a sample, you could stack a number of these up and just form a phantom sample and measure the dose as a function of thickness. They're reasonably independent of dose rate, atmosphere, and temperature. These are important. At least dose rate does not vary too much for industrial applications. The atmosphere can be harsh. Ozone is always generated in when you pass the electron beam through air, and so you will always have some ozone present. There will be various oxides of nitrogen present also from the passage of the beam through air, and these will be present in small amounts. The temperature always increases in the sample when you radiate it, so it must be stable over a reasonable temperature range. Disadvantages to most of these is that they are sensitive to fluorescent lights. They must be stored in a black container of some sort that will protect them from fluorescent lights, otherwise they will give a false reading. Incandescent lights don't seem to bother them too much, but fluorescents are bad news. The uniformity of the dye or coating, the dispersion of the dye in the material can vary somewhat, and this of course is out of our control. It's just the manufacturer to keep that as uniform as possible. And as I alluded to before, the interaction with ozone or other chemicals in rubber could be a problem. Generally what we do is put these films in a plastic envelope or a ordinary envelope, even anything, just protect it from the surface of the rubber if it's on the rubber, and that way if there's any chemicals to be leached out of the rubber, at least it won't affect the dosimeter in the short time it's held on the rubber surface. Well, so much for dosimetry techniques. Let's look now then at the effect of the energy on our processes. And here we're dealing with a different situation. And the energy, as I said earlier, determines the penetration in the product and also determines the distribution of the dose through the thickness of the product. Now, if we were dealing with X-rays, and that's what most people are generally accustomed to, you probably know that the energy would decrease monotonically as a function of thickness. For X-rays, basically, you would have pretty much a straight line decrease as a function of the thickness and the density of the material. This is not the case with electrons. Electrons, you go through a peak in the dose somewhere in the 1/3 to 1/2 the way through your material, depending on how thick the material is and what the energy is, of course. I've plotted here the dose distribution through as a function of thickness for various energies, 200 kilovolts up to 1,000 kilovolts. The crosshatched portion here is the amount of the energy that is absorbed passing through the window on the scan horn and also the air between the window and the sample. The window does scatter low energy electrons to a large degree and absorb them. So it's very significant at 200 kilovolts. At higher energies, it becomes less and less significant, of course, because it's a constant factor. It's rather independent of the total energy. As you can see here, the useful range then, say at 400 kilovolts, would be from here to somewhere out in here. So we're talking perhaps 500 to 600 milligrams per square centimeter of thickness. By the way, this thickness is expressed in the actual thickness in centimeters multiplied by the density of the material. That will compare the various materials on a single scale. The maximum energy, I said, would be 800 kilovolts, which is slightly higher than this, and there you see we would have a total penetration that would amount to about 200 to 250 milligrams per square centimeter of useful penetration. I've illustrated here the same type of curve, but for 800 kilovolts, and I've also superimposed on here the thickness of a standard passenger body ply material. 60 gauge body ply would absorb this much material. This would be between the window and the air. And this portion under the curve would be wasted energy in this case. It would penetrate through the product, go into the floor or something, whatever was under the product, and be wasted as far as our process was concerned. The total range that in various samples as a function of the energy is shown here for a single side irradiation such as I've described in the past couple slides. At 400 kilovolts it would range 30 to 40 mils on up to close to 100 mils for 800 kilovolts. This actually is the range where the entrance and exit dose would be equal. You would still have a tail of energy above there, so if you really want to go down to zero, you can pick up a few more mils, but this is assuming that we have equal dose on both sides. If one irradiates a sample from both sides, then of course you can obtain much thicker penetrations, and it's not just twice as thick, it's actually a factor of 2.2 to 2.3 times as thick, because you would add the tails of the two doses from each side, and this would give you the added 10% or so of range there. I'd like now to show a few of these curves. These are calculated as a function of the thickness of the material, the product material. Assuming here we have a body ply with a density of about 1.14. And I'm plotting here sample depth from surface A to surface B, and a relative dose then that would be deposited in that sample, assuming we had 800 kilovolts and we were radiating this material from one side, one surface only, surface A. And the previous example I showed you was 60 gauge material, and the curve, as you see, comes up and is slightly lower on the B side than it is on the A side. As you increase the dose of or the thickness, of course, the back surface would have a lower and lower dose. As you decrease it, you approach closer to the peak of the curve, and at 40 gauge, you have a rather different distribution than what you have at 60 gauge. The configuration that one can actually use then under the scan horns to achieve various distributions of dose of material are envisioned here, and these are somewhat similar to what we will be using. If we, first of all, use a multiple pass arrangement, that eliminates that wasted energy that penetrates through the material. You soak it up in the second pass, and therefore you're somewhat more efficient. In this case, we have here one scan horn, here the other scan horn. We're passing the material under. Surface A is irradiated by both scan horns, both machines first, then passes over a pulley and comes back, and after penetrating through the material, then surface B would be the one facing whatever beam is left, and then the beam would decay in this second layer usually. For most of our products, only when you get down in the range of 40 mils or thereabouts does any of it get through the second layer and start penetrating the third layer. If you do not want to irradiate the same surface with each of the horns, a configuration like this would be available. The product will come in from the rope between the two scan horns, pass first over this set, and in the process of passing over the surface is reversed. So the surface A would be facing this material, or this horn, the surface B would be facing this horn. This way you can get a symmetrical dose distribution as a function of depth, as I will show you in another slide here. The configuration that we are planning for Wilson will have an arrangement similar to this, where we can use either of these. If you use this configuration, you essentially would pass A right through here, through the back, another pulley here, and through again. Or if you come in to the center, you would follow this configuration, have one surface irradiated by one horn, the other surface irradiated by the other machine. If we then utilize the upper of the previous configuration, where basically we have two passes, we're festooning the thing, so that it's picking up all the extra energy, and side A is closest to each of these. We can get a very non-uniform distribution across the thickness of the material, depending on the gauge. You can see here that at the 50 and lower gauge, we have over 2-to-1 difference of dose from one side of the material to the other. This might be very useful for some of our body ply applications. We may very well want a gradient of dose across the material. We aren't totally sure of that yet, but we have to do more development studies to find out just what the final configuration will be. But this is readily then obtainable from the configurations that we plan. At higher gauges, as you see, this would tend to level off. You have a fairly flat distribution of 65 gauge over about half the thickness, and then a gradient through the rest of it. The most uniform type of distribution, of course, is this one, where we radiate both sides. One horn hitting side A, one hitting side B, and again festooning, so we pick up the tails. And here you see then you have a symmetrical distribution in the range of 50 to 60 gauge. It's quite flat. Peaks as you get down to the lower thicknesses, and again peaks somewhat at the higher thicknesses. Again, as you see, all of these curves were normalized to a relative dose of 1 at the front surface. But when you start festooning these things and picking up the tails that are penetrating through the products, and particularly as you go to lower thicknesses where you're penetrating not only 2 layers but sometimes 3 layers, you are gaining considerably on the amount of dose on a relative basis that's deposited in the material. Instead of having a value of 1, you're up in the range of 1.8 here at the surface, which just says that we're making very efficient use of our radiation and not wasting it as we go to lower gauges in this manner. So much then for the effective energy on the product and the material configuration. We'll deal now with some of the interactions that actually take place when electrons impinge on rubber. Simplest way to describe this is that just about anything can and does happen. At these high energies, there are enormous amounts of excitation, ionization taking place, scattered electrons, ions, what have you, free radicals, secondary electrons, breaking of chains. All of these can occur. The one process that we're interested in having occur, of course, is cross-linking. We want to incorporate a few cross-links in the material to act as a precure to stabilize the form of the material while it's being assembled for final curing. At the higher energies, the utilization of the energy for cross-linking and for chemical reactions is very low. There's just too much energy in these electrons, so they have to be slowed down considerably and their energy decreased before they become very efficient. And actually they have to be slowed down to the range of about 100 electron volts, which means that they're slowed down from 800,000 to 100 before you really have a high efficiency. This is the reason that you see the peaking in the curve further into the sample. Initially, when these things hit the surface of the material, there's some scattering takes place, and as each primary electron interacts with the material, it loses a little bit of its energy and perhaps changes direction a little bit. And for each time it interacts, it loses some more, and as you go along, you get a cascading effect. The dose is built up because as the energy gets lower, it gets more efficient. And then eventually, when you penetrate far enough, of course, then there's just a monotonic decay of the further interactions as they penetrate to the final depths of penetration. There is a considerable amount of heat generated in any of these processes. Theoretically, for rubber compounds, one would expect a rise of 6 degrees centigrade for every megarad of dose deposited in the sample. This would be assuming no heat losses of any sort. Of course, we always have some conduction losses, convection losses, so the actual temperature rise will be seen to be somewhat less than this, but one must consider this, and you must, in some cases at least, incorporate cooling of the sample after the radiation, similar to what one does on our calendars now for, certainly for tread flies, also body flies. The types of cross-links we're dealing with here are carbon-carbon, rather than the carbon-sulfur that we normally have in cured rubber materials. The free radicals are formed by the interaction of the electrons. These then combine when two free radicals get in the vicinity of one another on different molecules. They combine, form a cross-link, and form eventually a three-dimensional network. In conventional sulfur curing, you always have a sulfur or a chain of sulfur atoms forming the link between various molecules. As far as the physical properties of the two, we've made a number of measurements on these over the years. There's basically no difference in the properties, whether they're carbon-carbon or carbon-sulfur. There is a difference between various rubbers as to the yields that one obtains of cross-links during radiation. I've shown here the G values for cross-linking and the ratio of the G-value of precision to G-value for cross-linking. The G-value is defined as the, the number or the yield of a particular process, in this case crosslinks, the number of crosslinks that will be formed per 100 electron volts of energy utilized. In the case of natural rubber, the G for crosslinking is 1. The ratio of precision to crosslinking is 0.1, which is good. You don't want precision in our process. We want as much crosslinking as little precision as possible. Polybutadiene crosslinks somewhat more efficiently than natural rubber. And again, the ratio of precision to crosslinking is about the same. SBR, generally the crosslinking is about the same. Precision rate is somewhat higher, however. Polyisobutylene is an example of one that is a bad actor as far as radiation. It primarily scissions. As you can see, the cross-linking G value is very low. Precision, or the ratio here, which is mainly scission, is very high. In general, when you have a molecule which has dangling pendant methyl groups or bulky groups, they tend to scission at the tertiary carbon where the branching takes place. Polyisobutylene is a prime example of this and is the most commonly encountered one. This then, of course, applies also to butyls and chlorobutyl and bromobutyl rubbers, since there the polyisobutylene is the main rubber, the main polymer in these rubbers, and there's just a small amount of isoprene or halogenated isoprene added to form the chlorobutyl or the bromobutyl. And because of the small amount of isoprene added, there is some cross-linking that occurs at low doses simultaneously with the degradation of polyisobutylene. It is possible to irradiate these to low doses and get a beneficial cross-linking, small beneficial cross-linking, particularly in chlorophyll. However, you always also have simultaneously the degradation, and therefore we don't seriously consider irradiating interliners, for instance, anymore. With our 100% chlorophyll interliners and our 80% chlorophylls. We used to do this a decade or a decade and a half ago in Plant 2 when our interliner only had small amounts of chlorophyll in it. And mainly had SBR and natural rubber, but the configuration we use now, it's not practical. EPDM, again, the cross-linking G value is similar to what we see in the earlier cases. And here the scission is even somewhat lower than what we see for polybutadiene and natural rubber. We have looked at EPDM, of course, the possibilities of radiating that in our roofing materials. The problem is there that even though this looks good here, in our roofing materials, we load that stuff up so much with oil and carbon black and anything else to make it cheap, and these are all high inhibitors that are really impractical to, at least at the moment, as far as we see it, to radiation occurring.
What's the ratio number over the right again? You keep calling it?
Scission to cross-linking. In other words, there are two processes that can occur. Cross-linking, of course, you combine two molecules, they go together. Scission is where you break a molecule instead. You basically break it down, you degrade the polymer down to lower molecular weight until it goes far enough, essentially, to the soup.
So you need low numbers over the right.
Right.
I had a question on the interliner. You said it's not practical for the 100% chlorobutyl. Is it practical for lower chlorobutyl, like an 80, 82.5% chlorobutyl?
82 is essentially the same story. The earlier days when we used a 20% chlorophyll, we could get by with it. Prior to the days of the radio, pretty much, we were using about 20%. And Goodyear basically has been doing that over the years, apparently. Their interliner has been very low, if any, butyl and mainly natural rubber and SBR. And they have been radiating their interliner.
We haven't given up.
Well, we haven't given up, but
I still think that we can irradiate at some low dosage and still get some benefits.
Why not go off chlorobutyl?
The permeability, then you have to start increasing your...
If it's radiated?
See, that doesn't affect
He's saying that's
permeability,
what
you see
Goodyear
irradiation. Radiation
Did I
has no
hear him?
impact upon permeability.
Are you saying Goodyear is still using low curve chlorobutyl and radiating their interliner?
As I understand now, they're starting to change over to the other one, but Al would better know on that.
Yeah, they're starting to increase their chlorobutyl because they can't meet the GM permeability test.
Ah.
But then they are probably also stopping the radiation of it as well.
So what I'm hearing is basically interliner is out as we know right now, right? Other than this, it's basically out, so I think we'll work there.
Well, we've run some tests in Canada actually, and we didn't see a lot of degradation in the chlorobutyl.
Is it out or is it in this future plan?
Out. It's out for the immediate. It's still an active item.
Okay.
You know, I'd like to one other question. It may be out for passenger, but it may not be out then for tubeless tractor tires where you don't have to have the high.
As long as we're over 30 or 40 parts of halogenated butyl, we probably won't consider it. Maybe a low priority. Now, if your fan ply insert is a non-halobutyl compound, certainly for their barrier strips, inserts, body ply inserts, certainly.
That's the way, Bill. You work on these guys, get them to think something other than passenger tires. Because that's all.
This is a heavy-duty plant as well.
We gotta get them into the stream here.
Admittedly, most of us are biased towards passenger tires.
Oh, absolutely. We're well
Not
aware.
all of us.
We're well aware. Chuck is an exception. Chuck's an exception.
He's also a very good exception. I'd like to illustrate here just some experimental data on what happens during the pre-cure of, again, passenger compounds. These are the stress strain curves for a body ply and a glass tread ply skim. As plotted here as a function of the radiation pre-cure dose. As you see, the green strength does increase almost linearly in this case with the dose that we have deposited in the material. Generally, somewhere around 4 to 6 megarads is the range we're talking about here. Here we see that at 4 megarads we have basically increased the green strength by about a factor of 3 to 4. When we cure these materials then with the final cure, the effect of this change is very little seen on the final cure range. You can see here, this is the cured tensile of each of these, and continues on up. I just didn't bother to carry the curve up that far, but as you see, the scatter is very small here, much smaller than what you see here in the range of the pre-cure. And so basically, the pre-cure radiation has small effect on the final cure in this case. The thing we're looking for, of course, is to decrease the flow of the material by doing this pre-cure. And here I have a plot of the creep compliance as a function of time and dose for, again, body ply, glass tread ply, and black sidewall compound. These all were essentially identical for this particular test, and as you see, as the dose increases, the compliance decreases, which is the direction we want to go. And again, this is on a log scale, so it doesn't look quite as dramatic, but several fold decrease in the compliance, and depending on the physical properties you want, one has to determine precisely how much of this is the ultimate for your particular compound. I'd like to say a few words about promoters and inhibitors. We're always concerned, of course, with doing the maximum benefit to our product at the lowest amount of dose, because then we can increase our throughput and or get by with less capital equipment and less machines to affect the process. So we're always looking for promoters to help us out. Historically, there are three general types that have been found. The first is alkyl or aryl halides. These are the chlorinated benzenes, anthracenes, naphthalenes, so on, and some of the polychlorinated compounds as well. They work quite nicely. Pentachlorobenzene is an example that works very well. Generally, if you put in a few parts of that, you can decrease the dose by at least a factor of 2 and sometimes more. Maleimids are another class that have been historically in the literature at least advertised quite highly. We've had less success in using them. We don't seem to find them quite as effective as the halides. The best, as far as their action go, are thiols or polymer captains. They are quite efficient at decreasing the amount of dose required for a given degree of green strength. Unfortunately, all of these materials have one or two things wrong with them so that we can't use them. They're either toxic or they stink. And we use them in the lab, and we can survive with them, but in plant applications, people tell us that we can't use these because they are on the toxic list. Thiols nobody wants to use, because once somebody opens a bottle of those, they drive you completely out of the building with the smell, but they are very efficient. We continue to look for innocuous ones that work well, and so far we haven't been too successful, but we can continue. Inhibitors, on the other hand, are very easy to come by. Unfortunately, are present in rubber at all times, it seems. Aromatic oils are quite bad, and these are used in our compounds. The usual aromatic oils that we use in tread compounds and some of the other materials are quite inhibitory. Antioxidants generally are inhibitory, particularly economic ones. Various heat cure ingredients that we use are sometimes inhibitory, sometimes helpful, and it seems to be a synergistic type of thing that varies somewhat with the compound they're in. We tend to do some more study in this area. We don't really know why they behave sometimes one way, sometimes the other at the moment, but I'll illustrate at least one example of this in my next slide. This was a little test I ran a year or so ago on passenger body fly, just to look at the effect of the various heat cure ingredients and see whether they were inhibitory or helpful. The master batch, CY157, the response to the tensile strength to dose is illustrated by curve A. The final material, CY157, is curve E. As you can see, it requires almost a doubling of the dose to obtain the same tensile strength in the range that we're talking about here between the master batch and the final. Adding each of the various finaling ingredients to the master batch one at a time, first the Cyrez resin, which is used, gave us curve B, so that shows that it was somewhat inhibitory, but it wasn't the whole story. Adding the accelerator gave us curve C, which almost superimposed on the final body fly response. Adding the sulfur, formula 675, gave us curve D, which was actually, in this case, somewhat of a promoter. Then finally, of course, when we combine these, we see that curve D and curve B are essentially canceling one another and having little effect, and the main inhibitor here in this case was the accelerator. As a further example, I've illustrated here the effect that we would have in CY157 by adding, I believe it was 5 parts of pentachlorobenzene. As you see, we then basically simulate what we see in the master batch at higher doses that even goes higher. So that the pentachlorobenzene in this case, if we were allowed to use it, would have essentially given us about a 2-to-1 benefit. I have done similar things in the past with a tread compound and found opposite effects. In that case, the accelerator didn't seem to have any effect, or perhaps slightly helpful, and the sulfur was inhibitory, so it does seem to vary with the compound you're dealing with.
Let me ask a question, maybe this is for time. What effect does all of this have on sort time in industry? Did we actually go to a longer scorch time?
Ed will actually answer your question in one of his slides later on.
Review that later.
Thank you. He does estimate it directly on that. Finally, I'd just like to finish up by saying if anyone wants to do any further reading on this area, we did publish a review paper a couple years ago dealing generally with the radiation of elastomers, much more detailed. Also, there has been a paper published by Radiation Dynamics several years ago which deals more with all the physical characteristics of the penetration of electrons and the sort of things I was talking about earlier, and it goes into more detail. Thank you very much, and if there are any questions, I'll take them, or otherwise we'll go on to Chuck's log. Yes?
I was wondering about safety. You're talking about all this shielding. Will people in the area have to be wearing dosimeters or film badges, or is the shielding
The
going to be
shielding
adequate on
will be adequate so that no film badges will be required. Generally, it's probably recommended that the operators who are there every day still should be covered by them just to be safe, but you know, for company policy and so forth, that will probably be the case. But for personnel who are occasionally present, it will be a completely safe area.
For people that are equipped or qualified and under a program for X-ray, the same thing applies.
Right, right.
Any other questions for Dr. Tveekrem? Thank you. Chuck now will review the test on heavy-duty tires.
Go to those heavy-duty tires.
Mike, I just want you to understand that we in Akron Heavy-Duty Development have understood that you are a heavy-duty plant. And we have also understood that there's some real good attributes and advantages to Electron Beam Precure and heavy-duty tires.
Yeah, I want to thank you for your support of our position on this. That was very helpful, because without you guys, we would not have gotten second in line.
I'd like to discuss our project review work for Electron Beam Precure and heavy-duty tires. And what I'd like to review is the work we've done in AX483, AA3B biased truck tires, radial and biased rear tractor tires and farm tires, and some work that we are looking forward to doing in the A2 tires. Electron Beam Precure and heavy-duty bias tires are going to be focusing on eliminating the body ply inserts, eliminating the tie gum, and the modification of the body ply skim itself. And the reason we're able to do this is because, again, we're increasing the apparent viscosity of the compound through Electron Beam Precure, and therefore we are raising the viscosity and the stiffness, and we can safely eliminate the body ply inserts. And likewise, we can take out the tie gum. What we're looking at is a material cost savings of around $3 a tire. That's for a standard 10-20 Transport 1 long hauler, 6+2 construction. We're taking out the 6 body ply inserts here, $3 a tire. Our constraints are we must maintain the 005 minimum ply insulation gauge. And many of you are aware of the work that we did in Pottstown several years ago. We did attempt to eliminate body ply inserts. We thought we were in a safe position with Measurex. In fact, we were not, and we had to back off, and even today we're back on the body ply insert method. However, with the Electron Beam Precure, we have demonstrated that we can safely remove these inserts by still maintaining adequate ply insulation gauge. Our constraint, again, though, is the 005. Eliminating the tie gum, that's a cost savings of about 50 cents a tire. Again, our concern here is controlling the inner liner stock flow, make sure that we don't get inner liner stock up in around the body ply cords. Modification of the ply skim is something that our compounders are looking at right now. We have a program to eliminate about 20 cents per tire by modifying this compound. What we want to do is we want to maximize the use of solution SPR. And Bill, we already have one program here at Des Moines where we are attempting to maximize the use of solution SPR without electron beam based on the current corporate prices of our SPR versus our natural rubber. However, we want to optimize that a little farther with electron beam pre-cure. We think that we can control our green strength through the electron beam process and even reduce the amount of natural rubber beyond that level.
Does that mean there's no effective tack?
We think that there might be, and we can talk about that in a minute. This is a tire section. It's a pretty lousy picture, but what I'm trying to demonstrate is that we have built some tires at Hamilton. These are 11-22.5 long haulers. We are looking for a minimum ply insulation gauge of 0.05. These actual tires, and I think I have the tire section back at the desk, we actually attained about a 0.08 or 9. Again, the control section was much better than that. But what we are concerned about is in the control section at higher ply insulation gauge, we did have cord-to-cord contact. In the tires that we built to date, we have not seen cord-to-cord contact. So we think we have some good evidence to suggest that we are in a safe position to take out the body ply inserts.
Cord pattern is much more uniform.
We saw that initially in our tractor tire program. We'll talk about that. And yes, every tire that we've looked at has extremely good cord path and crown angle uniformity. And that's an attribute that we're going to rely on and see what other benefits we can get.
Chuck, is that midpoint measured at the 45-degree point?
Yeah, that is measured at the 45-degree point. Of course, when we were looking at the tires, we went from B to B, looking for cord-to-cord contact. But I have some gauge measurements. They were taken at the 45-degree point.
Did you guys pre-cure this tape that was holding up these things up there?
I think we should have, but we did.
Screw off the adhesion?
This is, again, a 1122.5 long hauler tire built at our Hamilton plant. What we were concerned here was removing the inner liner tie gum as a bottom insert on the first ply. Our constraints were to make sure that we were maintaining make sure we were not getting penetration of the inner liner compound up and around the body ply cords. This is the lap splice, the builder's lap splice, and this is an area that we're concerned because we do have some inner liner coming up into this area right here. It's a safe position, but we have some concern for it. The passenger people have some concern also, and they will be discussing that further. We feel that if we do get some inner liner contact with the body ply cord at that splice angle, that we could generate a crack here, that would crack down, and eventually could fail the tire. This is an 1124.5 transport one. This tire was originally scheduled to be built here at Des Moines, but because of a ticket problem, we did transfer that to our Decatur plant. This is just to, again, demonstrate the fact that we did maintain a pretty flat level of inner liner compound, no penetration up in between the cords. Again, we did eliminate the tie gum. That's about a 50-cent tire cost savings. And we were real happy that we did maintain a nice flat level of inner liner, no penetration. We want to monitor that farther, and we'll be talking about that again. This is where we really started in our heavy-duty program. We actually had a performance problem in our radial rear tractor tires, as you maybe recall. We were generating a crack up around the body ply cord that was cracking down. It was cracking into the band ply insert. It would eventually pinch the inner tube and fail the tire. We went into the electron beam process to again see if we could resolve this problem with electron beam cross-linking. In fact, we did. We were looking at improving our hours considerably past the 3,000 hour range on our Columbiana circle test. Since that time, we have resolved the problem in an alternate way. But during this study, we did build some tires. We saw extremely good cord path and extremely good uniformity in the tires. We're looking at a cost savings of about $3 a tire, and that's a material savings only by taking out the inserts that are applied between the body plies underneath the tread. And we also feel that we can get a real good ply gauge reduction here. We actually built 4 builds, I think, on the 18-4R38 tire. The second and third build, we were able to safely reduce our ply gauge from an 063 down to a counter gauge of 057. Now, looking at the tires, and they have completed our Columbiana circle test and our drum test, and we think we can safely even reduce that ply gauge another 10%. So we're going to be looking at that and probably getting some more specs into your department. So we are looking at ply gauge reduction, and again, we don't see any coarse strike-through in these tires. Again, we're looking for all applications of electron beam pre-cure that we can. In addition to the 2 main programs that we're really focusing on, we're also looking at the pre-cure of the abrasion gum strip in our A2 tires. And you can all probably recall the fact that we had the old roto-cured pre-cure, CA809, and we eventually got off that process and we went to what we call high Mooney stocks. Basically, they've been satisfactory, but we still have seen some problems, some shaper separations. In this program, we're looking at maintaining a minimum of 0.4 in the cured tire. So we don't know really where we're going to start at, but we have a 30-day build starting in July in our Bloomington plant, just to look at the effects of using electron beam pre-cure for pre-curing that abrasion gum strip component. Shoulder barrier strips. This is a program that Des Moines has really made use of. I don't know how many tires we probably have built, but it's been several hundred. We're looking at putting a barrier strip between the inner liner and the first body ply on tubeless tires, or on top of the first body ply in tube-type constructions. We've built several sizes here at Des Moines, and some of the problem size that you had, this appears to be the only resolvable method of eliminating coarse straining. Again, we're not convinced that's the only method, but we have demonstrated the fact that it is a very good method.
We gotta look at that further though for cost effectiveness.
Yeah, we feel it's about 60 cents a tire to...
I mean, maybe do the one ply instead of the barrier strips, because it's an extra operation and an extra building rate procedure, okay?
Okay. Again, we've got some 16.5, 16.1 ANSs running at Columbiana right now to demonstrate the fact that, putting the electron beam pre-cured component in the tire isn't detrimental to the tire service. We're also building some 11L15 farm tires in our Hamilton plant to demonstrate the same thing. We had a coarse straining problem in the tubeless tire there, and we had to put some barrier strips in. We think that, again, an alternate solution to this problem would be to irradiate the first ply only, or maybe the first 2 plies.
Yeah.
We are willing to look at that, and we can get some specs, into your plant to look at that. I will mention this, that we do have 4 rolls of gum sheet coming to your plant that were pre-cured in Shaw Industries 2 weeks ago. So they should be in transit. We got to get them through customs.
I could use it any day.
Well, we have to talk about a program to keep you supplied with that material until we can find some plausible alternatives to that program. We had some problems in maintaining insulation stock around the bead bundle and around the reinforced area. We've had considerable turn-up failures in some Decatur tires and some Hamilton tires and even some Des Moines tires. What we're looking at here is pre-curing the reinforced material that goes up and around the bead bundle. That'll maintain the insulation gauge, we feel, around the wound bundle and avoid that wire contact with the textile and eliminate those types of turn-up ply separations. Reduced cure is an area that we really haven't looked at, but our laboratory data has suggested that, in fact, by cross-linking with the electron beam, we have imparted a partial pre-cure to that component, and in heavy ply tires, tractor tires, A2 tires, we think there might be a significant cure reduction available. So we'll have to be looking at that. Some of the problems that we had in the Hamilton builds, we were concerned of processing. What does electron beam pre-cure do to our tire processing? We were looking at turn-up height changes, bias angle changes, tire shaping. By making this tire so rigid with the Electron Beam Precure, what does it do to tire shaping? We were concerned about that. Unfortunately, we've only built small numbers of builds, and so the amount of processing we have is limited. It suggests that we might have to make some modifications to our spec to adjust turn-up ply heights, maybe some bias angles, and maybe modify our shaping cycle in the curing press. Again, in relationship to the passenger tire where you're talking only 2 plies, we're talking multiple plies, 6+2 constructions where we have a more rigid carcass. We probably will want to add some work into A2 tires here. We probably want to take the technology of eliminating the tie gum out of our truck tires and use that same technology in the A2 inner liner. And we think that we want to start that pretty quick. You're on the 2-ply inner liner construction with the tie gum inserted at the bottom of the first ply. Is that correct?
No, we're not on that construction. Oh, yeah. Tie gum on there.
Tie gum on the bottom first ply. What we're looking at is removing that tie gum component altogether by pre-curing the first or maybe the first 2 plies of the tire, and therefore taking that component out. We think that could be a real good cost savings. What are we doing with Electron Beam? Well, Dr. Tveekrem explained that we are providing cross-linking and we're increasing the apparent viscosity of that compound. In the work that we've done here at Des Moines, the CA867 or the CA607 compound, we were able to raise from a Mooney viscosity green from 45 to 125 at a 5 megarad level. And that's a significant increase, and we think that's what is imparting the attributes to that project. TAC. We have seen some incidents that we are affecting the TAC level. And in our program to modify the skim compounds, removing the natural rubber, we think we will further alter the TAC level. Unfortunately, we had a lot of constraints in the work that we've done. We've had to count the materials here at Des Moines, ship them to Boston, re-roll them again, ship them back, unroll them, cut them, re-roll them. All this handling, we think, has been affecting the TAC level. So we really don't have a handle here, but you know, the literature suggests with the heat buildup that we are imposing on the product that we probably are affecting TAC level. Some of the input that we got back from your plant is that the tires build quite adequately without problems with TAC. Same thing in Hamilton. In other instances, we have seen some deterioration of TAC, so we're concerned about that, and our program is that our compounders in Akron are prepared to adjust the resin levels in these compounds to help you with some TAC problems. Again, we want to maximize the use of solution SBR in our skim compounds. That's not only a plant savings, but that's a corporate savings for the company.
That's not a plant savings, it's a corporate savings, it's a plant cost increase.
I'm told that at the end of the month that you do get a
That's only through November 1st.
November 1st?
Yeah,
And
your
you
new
have to
standard cost.
negotiate that.
Your new standard cost, actually, that we got to reflect that cost increase in our transfer price.
This is a problem area.
Supposed to work.
We're very concerned about where they're headed with that one.
Yeah.
It's got us very bothered because
That's the only way you can do it, though, is change that standard cost and the transfer price.
Okay. The fact is that the corporation
No, the better
does
way to
save
do it,
money.
reduce the price of the synthetic rubber as we paid for it, rather than this Mickey Mouse cost.
There's several
By the way,
alternatives.
Wait a minute, we have to tell you what happened here. We made a mistake. We sent Bill Frazier to a 3-day school
Mistake.
on accounting for non-financial managers.
That was a
Given
mistake.
at Drake University. And ever since he came back from there, this subject, he won't let it die.
He's an expert.
He's an expert, that's right.
Good.
But he's right, though.
He is right.
But he's right.
I hate to tell you, Mike, he still doesn't know a debit from a credit.
Yeah, this will have to be resolved with our financial people. The fact is that the corporation does make money by maximizing the use of solution SBR. So that's what our program is, and that's what we have to help you do. We do have a problem that we're concerned about. We don't know how big of a problem it is. But what we're seeing is we do see some degradation of the tensile in nylon, polyester, and rayon textiles. Looking at the rayon column, we have recognized a problem here even when we had the unit at plant 2. And for that reason, when we were building the rayon constructions, we didn't consider electron beam pre-curing body ply materials. We were limited to inner liner. Now our focus has just changed the opposite. But at the levels that we're considering in 5 megarad level at around 750 or 800 kilovolts, we are seeing degradations in the neighborhood of 30% in rayon. And of course, we do have some rayon belt materials here, and we have no programs at all to consider electron beam pre-curing for rayon materials. Polyester at that same level, we see a small decrease in tensile, and likewise for nylons type 66. Now this is not my data, this is data that Dr. Tveekrem supplied to me from O2 company that did some work. But 2 weeks ago I was able to resubstantiate some of this up at the company that we contracted to do some electron beam work for us, Shaw Industries. We did some more nylon. I did a nylon type 6, and we saw about a 4% loss here. Here we saw about a 3.5% loss. So we are seeing some loss in tensile in the tire cord. We don't think that's of any big magnitude, but we want to get some good data on burst strengths and plunger data to see just about where we are. These materials were treated in skim stocks, just like we will be proposing for the Des Moines plant. So what I'm saying is that we have some degradation. We don't think it's a big concern. We still think that the advantage of using the electron beam to eliminate the inserts and reduce ply gauge is overwhelming a good proposal, but we are concerned about our loss in tensile.
Coupled with a temperature degradation possibility, then it becomes serious. Or of more concern when you add in the possibility of degradation we saw with excessive cure.
Okay.
You're taking a safety factor out of it, aren't you?
Well, we have a program there. We are losing about 2% tensile loss with the electron beam pre-cure. And you're right, that is coupled with the heat transfer during the curing cycle. Now, basically in the radial ply tire, where we're seeing that degradation, is focused with the longer cure cycles that we have on radial ply tires. We have about 55-minute cures on bias ply, same shoulder. We have about 95-minute cures on radial ply tires. We have an active program in Akron right now to modify those compounds to allow us to go to higher external curing temperatures, which will drastically reduce the cure time of those tires. We're talking about going from a 90-minute cure back to the 60-minute cure, and we're proposing that by 11/1/84.
Wait a minute. Wait a minute. Do you realize what kind of analyses we're going through in this plant right now to figure out our capacity?
I am, and I was on the phone. And,
hey, Mr. Frazier, we just got into this the other day.
We just went through that.
Okay, I've talked to Dave. We are concerned about, rationalizing over to the radial type tire. And you're going to have to get automatic loaders and bigger curing presses, and we understood that. And I explained to Akron, I said, hey, this is a big dollar investment for the Des Moines plant. And I says, and it's ridiculous to consider maintaining a 298-degree external curing time when we can take advantage of higher external temperatures and get us back on the same basis. Because what you're going to be doing is taking, bias ply tires and replacing them with high numbers of radial ply tires, and we won't have the curing equipment or the available manpower to handle such a thing.
The figures I think we quoted were roughly 10%. I think it was 8%.
Well, here's my question. Have either one of you guys related all this to Gene Ricker or industrial engineering? Do they know what's going on? Because they're the ones that are working on this study, and they need to know this.
Bill?
There's Gene sitting back there saying,
in the work plan analysis that we supplied you for the Cure Rate Integrator, we massaged that and made that about a 4-point program. We were to use the Cure Rate Integrator.
That's right. The data that we've worked with Akron, and we've communicated with industrial engineering what is the latest thinking as far as what we're going to end up with cure cycle.
That is great news, though.
Our plan is to go to a 310 cure. We're going to utilize the Cure Rate Integrator in that program. We're going to reestablish the standard practice cure limits. We're going to move to a 310 external cure. We're going to accomplish our Columbiana Bardos crack testing in September, and we hope to give you approval in November 1. That's what our program is.
That's fantastic.
That will have an influence on the degradation that we're seeing in polyester and get us back into a safer level.
That's our program.
Possibility going beyond 310?
There's a possibility, and probably Ed, even though he's not representing the tractor group anymore, could probably give you some more data. You know, we saw significant losses in tearing and fire nose cracking at the higher temperatures, something that we didn't want to do in the radial ply tire. When you were at a 50 tire level, we didn't see that as a problem. I mean, curing capacity wasn't a problem, so we just stayed at 298. But the fact is that the industry is shifting drastically and quickly to the radial ply tire, and recognizing your problems to avoid, you know, tremendous increases in capital costs to modify equipment with automatic loaders and curing presses, we felt that we had to get the Des Moines plant over to a higher temperature cure to reduce that cure cycle. Just had to.
There's another thing happening, Chuck, which I think is relevant. You know, one of the reasons for the shift is Goodyear cut their price dramatically last year, and we followed suit to where the radial tractor tire is now only 10% higher than the bias tractor tire. That has made our tire unprofitable also at the plant. So the items that you're showing on the radiation or the electron beam pre-cure are very, very applicable. Extremely helpful to get that cost back down so that the tire becomes profitable again.
Okay.
Those are good ones you had in there.
Again, those costs, can't find the slide right now, but those are predicated on simply a 10% reduction in ply gauge and removing those inserts that we have, you know, put in over and above the USA spec to resolve some processing problems. So that just gets us back to par, and that takes about $3 out. Now, anything we can do above that is going to save more money. And we have some good experience there. I mean, this is where we started our work. We got into the program later than our passenger people, and that's where we started, and we started to resolve problems, not to make cost savings. But the fact is that there are a great deal of cost savings to be gained in there. So yeah, that's what our direction is. We're here to, you know, try to help you people.
So you listed the projected savings for truck at $370 and tractor at $3. What's the processing cost for the plant going to do those numbers?
Okay, again, those were material savings only, and there'll be some positive and negative effects on that. Number one, eliminating the compound from the tire is going to increase reduce your overhead and increase your available mixing time. So that's going to affect labor overhead right there. The fact is that you will have to add labor to process through the electron beam. So there's going to be some negative and positive effects. I don't know how they're going to be balanced out. That's something that your cost people will have to
we've analyzed
address.
that.
Those were analyzed on the DCFR, and it came about 25%, right? Taking all these into right.
It's very positive for us.
So you have a DCFR of 25%.
Russ?
Is there a possibility we're going to get a more stable green tire, radial tractor tire out of this?
More stable green tire?
Yeah.
We think so, and that's been demonstrated in our passenger group, and I think Ed will talk about that. They have demonstrated, or maybe Al will demonstrate that we have achieved a more stable green tire. Yeah, we expect so too. The 6-ply truck tires that we built in Hamilton demonstrated that, to the point where we were concerned was that going to restrict our tire shaping. We did restrict some pantographing, and we had to adjust considerably our turn-up ply heights and cut ply widths. In fact, we over-adjusted, and now we're a little bit in trouble. So we've had a lot to learn. I want to be front with you.
You know, there's another area we didn't even figure cost savings.
What's that?
Ply width.
Reducing ply width.
Yeah, well, no, we put extra width in to handle it through the system for pull down.
Oh, no.
This material is should not pull down.
It should eliminate pull down or remain the same.
We don't even have that in a cost saving.
So,
Chuck, are you finished?
yes, I'm trying.
Where's the system? I see a picture of the system up there. Okay. Your handout.
I didn't show that slide.
I want to discuss the let off.
That'll be discussed
Okay,
at the
that
end.
will be discussed. I want to mention, in regard to the system, what we got is basically Jim have put some layout which is similar or close to the layout of Wilson plant.
okay? However, detail in regard to the design of the let-off and all that, we are thinking of coming back in a smaller group and get together in regard to see what Des Moines plant requirements are to be, okay? We are thinking of coming here the week of June 11th.
All right, but I'm concerned about the let-off, okay?
Okay, Ed will,
Standard practices with compliance and so forth. It's gotta be discussed.
we'll talk about that.
All of your pictures were on electron beam treated material.
Yes. There's a tire section on the desk if you want to look at that.
Right, I see. Okay.
Any question for Chuck? Pardon? Okay, why don't we take 5 or 10 minutes break and then
Well,
Go ahead and focus there. Okay, here's step is on.
data we have done on pre-cure material and also on the electron beam.
Okay, I'll quickly review with you information and tests that we have done to date on this electron beam procuring and the process engineering viewpoint. This is a summary. There's a 3-page summary that we gave management for the board review of these projects. And basically, procuring the body ply and body gauge retention was the big factor. We're going to have less gauge variation and whatnot. We're going to do this. We're going to remove the tie gums or the inserts in the, we're talking about now the passenger and light truck tires. And we have about a 95% confidence factor that we'll be able to remove the tie gums and the inserts in our tires and still maintain good inner line of body cord integrity. Another plus that we see is that in green tire, that in M2 type building, you're going to have less carcass collapse. You scan in the first stage carcass on itself, particularly some of the large sizes, you get some rather radical, drastic collapse of the body. By pre-curing the body ply, we give it some guts and it tends to keep the carcass more intact, less prone to collapse, even after several days. This is based on actual trials in Wilson. Body ply, shelf life, we don't see any significant difference in the dosage that we've looked at, and that's between 4 and 6 megarad dosage. Those numbers in parentheses are the number of trials, projects that were involved in trying to establish that parameter. We recognize that some of the higher dosages will affect TAC, but we feel that at the dosages we're looking at, the 4 to 6 megarads, that we're going to still maintain adequate TAC in tire building. In fact, in our Wilson build, the most recent build we had in Wilson this year, the comment made by the tire builder said that, in fact, that the material that we had pre-cured had better TAC than the control. Splicing technique. We have some concerns in the splicing technique. We have seen in our tire testing that when you, in the assembler splice and the builder splice, if the cord gets bared and we get inner line in contact with that cord, we tend to get, and I think Chuck alluded to that a little bit, is that we get a crack initiated, goes down through the inner line, and get an inner line of crack. So there is an area of concern. I'll talk about that further in what we're planning on doing and what we've done. To get some tires actually for test, we have actually pulled that wild cord off, and we had no problems with those tires. I'll go into details on that a little bit later. Product performance, these are the type of tests that we have conducted on passenger tires, high-speed endurance beats, inner line of crack, and we find that all of these are equal to or better than the controls in the pre-cured tires. I'm talking about now the pre-cured tires where we're only pre-curing the body ply and we've eliminated the inserts. Fleet test, we've had one fleet test that ran 40,000 miles, RNF, run no failure. tires were taken off, no problem at all. We're going to recycle some tires in this latest build. These are earlier builds, 82, 83 builds, and 84 builds. The one, the Wilson, those tires are going to go on freight test. We have just started on this Wilson build in late, we started applying tires on commercial in California. The tires have passed a pre-screening indoor test. Ed will sort of give you more details on some of the more recent tests on this commercial build of these tires in Wilson. Other components that we've looked at, and again, we're feeling our way through this thing. There were some tests where we pre-cured the stabilizer ply in the belts, and we were talking about gauge retention. We find that there's about a 20% better gauge retention in the pre-cured tires. We've got to optimize the radiation of steel belts. We don't know everything about it. This is an area where we're going to have to investigate. Once the Wilson system is in place, again, like I think Chuck alluded to, is that what we've had to do is calendar material, say in Albany or Wilson, split the fabric because the units that we were dealing with only could take 36-inch max, and so we had a lot of problems just running it through the factory. We had to double line the material. In Massachusetts, some of the early work was done there. They went, this was high voltage, they went out of business, and we now are doing most of our experimental work up in Canada, irradiating it up in Canada. So getting the stuff from the plant into the proper liners, up to Canada, irradiated and whatnot, and then bring it back to the plant has caused actually some, I'm sure has had some impact on some of these tests.
Is there a possibility of getting gum wedge out if this is satisfactory?
That's what the whole program is. I think ultimately, once we get some better definitions, and once we get the Wilson system going, I think that's definitely, we're going to be able to retain gauge on the belts and maybe be able to eliminate the wedge. We have even tried pre-curing some treads, and this was predicated on some research data that indicated that if you pre-cured treads with electron beams, you improve the rolling resistance. We tried that, or my predecessor tried that, and based upon this limited trial, we didn't see any advantage, but we're still not dropping that as a possibility of getting a little bit better rolling resistance through electron beam pre-curing. We have tried pre-curing the abrasion inliner pre-assembly. We had a trial up in Joliet trying to see if we couldn't retain the gauge of the abrasion gum strip and also probably impart some chafe resistance, get that W3 that we're up against right now, trying to maintain that 05 gauge in the cured tire. The trials were inconclusive. We had some other problems. We did try 100% chlorobutyl and bromobutyl. And really at low dosage, that's why my answer to you, Bob, was that I've not dropped actually even irradiating 100% chlorobutyl. At low dosage, we did not see any degradation of the polymer or the compound at low dosage. We still haven't got, this is just a one-shot deal we were trying, and I think that definitely would be something that we want to keep on the books as a potential cost savings where we might be able to retain gauge of the abrasion gum strip and meet the tire engineer's parameters of the 05 for this particular critical gauge in shape.
Well, the abrasion gum itself,
yeah,
it should be more receptive to electron beam, or is it too low?
We don't, we've not done enough work to really define that yet, but it doesn't have a lot of oil. If aromatic oil is an inhibitor, certainly this doesn't have a lot of oil. It's stiff, as you well know. It's
that's the piece we're really talking about, right?
That's what I really want to irradiate, and we could configure the an electron beam system where you wouldn't irradiate the center where the inliner was and only irradiate the edge. You'd be wasting all that middle part, but you could conceivably just irradiate that edge where the abrasion gum strip were, and then impart some more green strength to that material so that it doesn't squeeze out as much when you cure it. Good, sure. One of the things we addressed also was potential impact on the process system. I talked about splicing, definitely with pre-curing. We inhibit the stock flow around the body cord, and when you talk about actually a wild cord, you don't have stock that's flowing around that cord. You could get some inner liner up against it, but we know that that gives us a problem. What we're going to be looking at is off-balance pre-curing, pre-curing one side more than the other, or leaving, actually, we've got a lot of ideas. You even get an off-balance body where you pre-cure one side more than the other. Definitely, we've got to come up with a resolution to pulling the cord. That's not practical, or really it's not cost-effective at all in the entire building. In-process storage, based on limited trials, we do see a slight reduction in TAC, but we don't think it's substantial enough that it's going to give us a problem at the dosages we're looking at. We're going to have to establish some aging guidelines and what's going to be the shelf life of the material once it's pre-cured. Green tire handling, I already talked about that. We feel that definitely first stage modified carcasses with the pre-cured body will tend to collapse less. One of the big problems we're having in Wilson is this collapse of the bodies in the first stage carcasses and possibly impacting upon GUO and tug uniformity and all these other parameters.
Now, there's a couple items coming to my mind. You know, we're looking at mostly advantages.
Yeah.
And I think the other side of the coin also.
Sure.
Pre-cured material in the stock cutting process for bad piece removal.
Mm-hmm.
I think we better be looking at that. How will that affect stock cutting department? Bare spots in the fabric, you know, where it's easily torn out.
Yep. Yeah.
It's not going to be easy. It's not going to be as easy with this material.
Exactly.
Burn stock areas, okay?
Right.
We got to think about that and how it impacts our other processes also. What about steel cutting? Steel cutting of an electron beam treated material versus our regular material. What's that going to do to us cut-wise at the banners and in the building process? Is that going to have a detrimental effect?
With the limited with the limited trials we've got, we don't feel it is going to be, but then that's something we're going to have to address. We don't know.
Start thinking about. I hate the hell to find out about them 2 or 3 months afterwards.
Right. In fact, I have asked the system that they've got here, the let-off system. There was some concern about flat spotting of the steel on this table. The rolls are just laying on this table here and fed down into the let-off of the pre-cure unit.
That's why I wanted to talk.
And I have, and I think Ed has asked the handling people to come up with a retrofit of the Wilson system is to support that roll so we don't get flat spot. Because once you get a flat spot, if you pre-cure, that flat spot is in there permanent. And so every time you come around, and even I think there was some trials run in Decatur where they found that the type of liner and the age of the liner, how if it's an old liner versus a new liner, how tight that liner was up against the even the polyester. You get, if it's not tight, it's loose, you're going to get an egg-shaped type roll, and you're going to have probably some looseness or some squeeze down on the top side where a lot of the load is being carried.
I'm concerned about the let-off, not as much about the kick-out. Okay.
That's right. Yeah. Once it's down here, it's not going to bother you. So you've already imparted some cross-linking to the material. It's up in here. Right now, you don't leave your steel galloned material on the floor any length of time because I think probably you're going to experience some flat spotting.
We don't put it on the floor here.
Yeah. Yeah. 100%. So that was one of the concerns that we had in the design of the system. But when we caught it, we recognized it. It was beyond the design point, and we're just asking to, in your system, if that becomes an important factor, definitely we would have a support.
I sent that in 3 months ago.
Pardon?
I sent that in 3 months ago.
Right.
When I first saw that layout.
Yeah. Oh, it was recognized actually, and it's in the subsequent units to Wilson. If it's necessary, it will be supported actually instead of this.
Everything is, unless you tell me, I don't know what you recognize. If I see it,
yeah,
and I'll ring it down.
Sure. Okay, stabilize apply. We need more trials. We will be doing some more work before the Wilson system comes on stream. Hopefully it gets at least some preliminary indication or some answers prior to their going online. Abrasion inliner, I still feel we should be conducting some more trials to optimize the dosage to see if we can't get some advantages in the abrasion gum strip retention of the gauge, and just throw in the sidewall BI pre-assembly to improve gauge retention is one of the goals that we have. One of the things you got to remember now is that when you get a pre-assembly, and if you're going to pre-cure that thing, if you got any scrap material, that stuff is par cured. It's virtually scorched, and you're not going to be able to throw that in as TMA. And one of the things that we've got to face up to is that the material, the green pre-assembled material, is going to have to be in such a condition, actually, that you're going to be able to put it in a tire. Because once you pre-cure that thing, there's no recovering it.
Al, have you thought of running a trial with just doing the abrasion to see if that solves the problem that we have in the rim flange area?
That's one of the things that, yeah.
Quit screwing around with the inner liner. We can build a tire with just the abrasion,
Yep.
and I'll give you your answer.
Yep. And there was a question that came up on commonality of tires. This was more for OE, that we do not tell Ford and GM some of the details, like, you know, do we or don't we irradiate and whatnot. And there was a VP that had asked the question that we could have a problem with Ford and GM not telling them or telling them some of the tires are going to be irradiated, some of the other tires aren't. It's not a concern. Okay, here's some of the details of some of these tests that we just reviewed. That was a summary. In November '82 in Albany, we ran some trials on body ply, eliminating the inserts or the shoulder strips. These are the indoor tests, results, and the conclusion being then that was also the trial where we ran a fleet test, a variable 3P, that's a type of test, that a type of sequence they have in the fleet. And that was the run no failure test that went completion of the test without any problems. Conclusions are that the indoor and the fleet tires with the E with the little hyphen here, that's the Electron Beam, pre-cured body ply, are equal to or better than the controls. We did experience some reinforced seps in the experimental tires, and we feel that that's this tack thing that we definitely got to resolve. Actually, we've got to have good, adequate tack in the building so that we don't get any problems actually in the cured tire in the field. Cord uniformity and reduced inline penetration was evident. We did retain our inline gauge with the pre-cured material. Again, in Albany in April of '83, there were some 5 specs. We were looking at 2 different body compounds. The first, CY157, is a current body radial skim stock, and the CY027 is a low-cost radial candidate. Built some tires, and we ran through indoor. Fleet tests were not scheduled. Based upon that data, and I'm not going to go through all of this here, but there are some pass-outs. I have a limited number of them, so that if somebody wants a copy, just find somebody that has. There's one in the book that we're leaving with Jim here, so if you want to make a copy of this information, you're more than welcome to this. The conclusion is, based on the indoor test, the Electron Beam pre-cured tires with the current body compound was equal to or better than controls, but we found that low-cost body skin, CY027, wasn't as good as the controls. We don't know exactly why. We're going to be looking at trying to find out what's rationale is, why is the CY027. I see Ed here has some ideas.
That CY027 has a tremendous slug of aromatic oil.
Okay.
About 21 parts.
21 parts of oil.
Say it's a low-cost body skin, that's what it was.
Okay, so that's probably the rationale, is that it
Remember
inhibited.
Jim's inhibitors, there's one of them was aromatic oil.
That doesn't mean we can't probably work around that too. I mean, you know, we can give us probably a higher dosage. We could try several other things if we choose to go to that CY027.
Well, but somebody that had a low-cost stem, if I'm reading this data right, looks better than the CY.
In some instances it was, but I think if you look at it overall, the low-cost skim, when you look at all of the tests, is not as good as the control. Inner line of penetration was acceptable in both skims. I'll be glad to review that with you. I mean,
want to take up everybody's time right now. This is our latest bill. Was in Wilson. We had a large P195 KABB tire, GM, and a P165. February of '84. Those tires are currently in indoor, and I think Ed will discuss the details of some of the tests that we've got finished now. The P165 ADR13 is on commercial in California. We're going to be putting on the other P195s, and also we're going to run, I think, the P195s at the fleet, just to get some background. We want to get some commercial data before January of '85, in to see what is it going to, what is this elimination of the insert and pre-curing of the body going to do for the real world tire, the tires out there in the field. Okay, the next item would be is that we did run some trials on the stabilized ply steel cord to reduce the gauge on Electron Beam pre-cure. These were tires were built in Albany in April of '83. Results of those tests is that indeed we see that we can maintain better gauge, actually retain better gauge on our steel when we irradiate one or better both sides, and the percent retention is over here. It looked like it's where the control was 114% retention on the irradiated material, on the pre-cured material. We're up around 143. On indoor tests, it was about equal. And a conclusion on this particular group of tires was the belt gauge retention from green to cured increased about 20%, i.e. conceivably we could reduce the gauge, the green gauge on our stabilized applies if we irradiated. We've got to optimize, we've got to do more work actually on optimizing what dosage we need for the pre-curing of the steel cord stabilized applies.
Or get rid of the belt.
Sorry?
Or get rid of the belt.
Or get in right, yeah. And I think that's gonna do both things. If we can maintain that gauge, the only wedge is in there to keep those ends up.
That's right.
And get that good contour. And I think if we can maintain better gauge control, cured from green to cured, we'll be able to get rid of those inserts. Tread BI, that was that improved roll resistance. The lab data said this would help us. These are the tires were built in Albany in April of '83, and we found that actually the results of those tests was that based on indoor, it did not have a significant improvement in rolling resistance with the pre-cured treads. Although that doesn't mean we're going to stop there. That's still going to be an active project. Rolling resistance being a very big factor for OE. BI gauge retention, we found that actually we had a 4 to 8% better gauge retention BI on the Electron Beam pre-cured material. The next group of tests that was run in Joliet, February of '84, this was that abrasion inliner pre-assembly. Here where we were irradiating 100% chlorobutyl and bromobutyl inliner. The conclusions were that the bromobutyl irradiated material and we did see some degradation in the bromobutyl inliner, but we did not see at the levels we were at. See, we're at a fairly low dosage here, so we're at the 1, 5, and 2 dosage. The chlorobutyl, we didn't see any apparent degradation, but really it didn't. The conclusion being that the irradiation, the pre-cured material is directionally better for gauge retention in the chlorobutyl inliner tires. We're not throwing it out yet. Probably with refining the dosage and whatnot, we might be able to see some advantage actually in pre-curing just the abrasion or the abrasion inliner pre-assembly. There are some tests scheduled for permeability tests of these tires, and for inliner crack tests, that's going to be starting this month, later on this month. Are there any questions?
Yes. All this looks very encouraging. In order to get to this point, we have to face the X-ray void experience qualification. I see nothing on this that addresses that.
X-ray voids?
That's right. Qualify the tire, do you get it out, put it on test?
All the tires were fleet actual X-ray. And
Indoor also.
indoor, and evidently the absence of the information, I'm surmising that actually we did not see, we wouldn't have put them on test, were there going to be, if they saw on X-ray some
Okay,
problems.
One of the disadvantages of this tag, I don't need any more goddamn problems with X-ray.
Right. That's right.
I mean, we need to recognize the problem
Okay.
even with the non-irradiated stuff. Present
At the present
Present
state of the
production
art
is a
here,
major problem.
it's a problem.
Mm-hmm.
Anything we do to worsen that aspect is only going to be more problems.
Okay, Ed, I think he has, I don't know if he's got some data right now, but on the tires we built in Wilson,
X-ray and holograph.
X-ray and holograph was equal to or better than the controls.
The pre-cured materials are equal or better than controls.
I think that'd be interesting if you had that handout, because
Okay, well,
Next time.
next time around, we're just developing the state. I mean, we just built the tires, a little bit ago, and getting them through X-ray and holograph.
hey, this looks good.
Yeah.
But that's
Now
really-
we've got some areas of concern, and like that splicing is definitely something that we're going to have to resolve before January of '85. I mean, we recognize that, and the reduction in tact is definitely something that we're going to be concerned about, and we definitely are addressing that. We're trying to address it early enough in the game that we'll have some answers before you people actually have on stream. Not. You heard anything on that?
There was something, I heard something,
We're talking about,
You talk about,
yeah, the let off rolls.
I have no idea.
I can check that.
Yeah, if you would.
Okay.
They, on our big tires, and the big bias tires, they lay on a rack, the big, non-form like almost flat.
Yeah.
Would this pre-cured fabric being stiffer have any effect on the tire as it comes back off the rack? You understand what I'm saying? Your green tire un-pre-cured now,
Tends to.
well, they flap, they have a pin rack that our big bias tires
Yeah.
are on. The tires almost lay flat, and I was just curious what effect that would have on the pre-cured fabric being, in effect, it's gonna be more stiff.
I would think we'd have more of a problem getting on the rack, and if they were on long enough and they sag, we're gonna have more problem with getting the tires shaped out.
Okay, I thought it'd be something we should
Yeah.
just think about,
Sure.
The third thing I want to ask about is knife life on banners.
That's what I was asking about.
I don't think
Knife life,
knife life on banners.
it's small, probably.
Yeah, I think there's not enough cure in the rubbers. I don't believe it's going to impact upon knife life, but it's something that.
Those are things we have to.
Sure, right.
Down the road.
Because you're going to be, because
if-
most of the knife
if you're-
life is going to be cutting is actually cutting
My-
through the material.
My point was, if you're doing more data collection, that while they're collecting the data, if they keep these other things in mind, then perhaps then the data can be collected instead of waiting until the problem exists
Sure.
in Wilson or.
Good point.
Well, if we're electron beam calendar rolls, then the knife life is effective.
Yeah.
Same way with the steel.
Yeah.
Same way in the third-stage building process when we trim them.
Yeah. Well, one of the concerns we had with this flat spotting was, what is it going to do to no trim? That was my concern when we started out. I said, well, we're trying to go to no trim construction, and if we have pre-cured a flat spot in several places along that road, what is it going to do to our taper cuts and whatnot?
But it has other advantages there. You won't get that distortion in the stitching process and building that you get now,
Right.
okay?
Exactly.
So it's got some positive things there.
Yeah.
Also.
But if you got a flat spot, you pre-cure that flat spot in there.
No goddamn flat spots.
Well, you can get a flat spot with just hanging that roll. You get a pear-shaped job.
We don't have anything pear-shaped.
Good.
I want to go back to the basic here for a second and then try to tie it into something else. We're talking about pre-curing is going to retain gauge. Now, the difference between green gauge and cured gauge is porosity.
Okay.
In other words, when we pre-cure, we are going to retain that porosity.
You're presuming there is some porosity, or there is.
Yes. Yes.
porosity, okay, yeah.
Now, when we pre-cure also,
That's assumption, but there's a flow factor there too.
It's the flow factor that's the concern, not the.
okay, that's kind of where I'm going to. If we have a step, let's say at the edge of a belt or at the edge of an SPI, there is always air, back to Bob's thing, built in here. Is this material going to be impermeable? Will it not absorb minor amounts of air? Or are we going to be trapping more?
The stock is gonna flow less.
The stock will flow less. Will it absorb less air?
I don't think it's gonna absorb any more or any less air. I don't.
The stock doesn't really
The stock
absorb
really,
that
okay.
material
it's the
anyway.
cord.
It's the cord
It's the
that
cord that
absorbs
absorbs the air. You get the air transmitted up a cord or up, the.
Okay, well, I'm concerned, let's say at the edge of an SPI, that I now have this little pocket in here and I've got
Yep.
pre-cured rubber on this. Is the air going to be able to flow, move away from it, or disperse?
Sure.
Okay.
I don't
Same
think it's
as it
gonna
does
change.
now,
Same
Charlie.
as it does now. In fact, probably might even be easier. Because, I mean, it'll flow to the point of least resistance.
I see no problem there. The
Okay.
cord still has that character that allows it to,
To wick out that air.
sure. I don't see that as a problem.
Any other questions?
They said I'm going to be covering the Electron Beam pre-cure passenger skim stock data. In particular, are updating the current build that we have in progress on testing from Wilson. First thing I'd like to go over, Bill just left, but is some of the green stock properties that Dr. Tveekrem and Chuck Allen have been alluding to. And the first column will be the pre-cured data, and the second column is the regular production of CY 157 skim and 053 gauge. And actually, we took calendar fabric and we stripped the cords out and did some of these tests. First one is 100% stress degradation, which is a green strain test. And what we do, we take a dumbbell sample and we stretch it out 100%, so it goes from 4 inches out to 8 inches, and we hold it for 4 minutes. And what we get is a peak curve that comes down then, and we get an integrated area underneath the curve. So again, the higher the peak and the higher the integrated area indicates a higher green strength in the material. And I've got a sample of each, the regular production sample and the pre-cured sample. You see a difference when they started out the same. I'll pass them around. You can do a little pull on them here. Don't pull too far. It'll pull apart. But you also notice that the pre-cured material goes back to almost its original. It has like an elastic memory that it goes back to after stretching it out. I'll pass these around. Just for a sample, you might perhaps we were talking about just before this for knife blade durability. You can see the difference between the two samples here and what the difference that you'll be cutting from regular production to pre-cured. Second test is another green strain test where we take the same sample, pull it out to 600% of its original length. But as you can see, because we used actual calendar fabric here, we cut the dumbbell to go across the fabric. We only went out to 365% and 340% for the non-pre-cured. But again, the numbers were higher for the pre-cured material. Mooney viscosity, in the stiffness of the compound, we went from a 45 Mooney up to 98 Mooney on the pre-cured rubber compound. You asked about scorch time. You see that on the regular production, we had 18 minutes of scorch. After we pre-cure it, it only has 11 minutes of scorch, so we lost 7 minutes of scorch time. But remember that the material is already calendared at this point, so we don't see this really being a problem. But it's indicating that you've got a partial pre-cure in it, and so it takes less time to finish it off to get your 4-point rise on the test.
The reason for my question initially was on some of the skims that we have a very short scorch time on, could we conceivably be looking at longer scorch times in the calendaring process because of the pre-curing?
Yes, I'd have to say yes.
I understood what he said. I understand that. Tell me, answer his question.
What was your question?
My question is, if in the final end product of the tire, okay, we have to have a certain amount of cure in the product. I'm asking, since we have a pre-cure unit, could we elongate the scorch time on the actual compound as far as the calendaring process is concerned, because of the pre-cure unit, going ahead and pre-curing the product before it goes into the curing process?
Okay, what's your answer?
Someone else want to answer that? Jim, you have any idea? Bill, any feeling on that?
Well, first of all, we don't recognize that present skims have short scorch times.
They do.
And
I don't even want to
secondly,
discuss that.
Answer the question. Is it conceivable that you could build in and give them that relief in calendaring on scorch time?
And make
because
it
of
up,
what happens
and make it up
yeah,
later.
Right.
It's conceivable. I'm saying it's conceivable.
I mean,
but
aren't we talking two different properties? You're talking a carbon-carbon cross-linking versus a carbon-sulfur with, you know, are they related at all? As far as the cured tire is concerned, I would think, without knowing a damn thing about that, it's not related, and no, there would be no relief.
But anything we could do in processing, relieve scorch incident would be advantageous, all right? So maybe it's something to think about, and somebody ought to be looking at that aspect. There might be something there. That allows you to increase your calendar speeds, and et cetera, which is all advantageous.
It'd be a lot of bucks if you could, say we're at 55 for CY and go up to about 70.
That'll give them something to work on another 10 years.
A lot of money. Be very good.
Rheometer properties, in the minimum is higher, the maximum reading is higher for the pre-cured material. Looking at your R value, you see we reduced the cure time by about 3 minutes on each of the peaks here, which we'll address here in the future programs. Green tack, we mentioned it several times. We brought back the calendar fabric samples from Wilson to Akron. We ran what we call a peel tack test. We put the two together, let them set for a while, and we pulled them on Instron. And the actual reading showed about a 3-time drop in the actual tack on the pre-cured material. But while we were building the material in Wilson, the builder said that it had equal, if not better, tack than the regular production material. So we've addressed it several times here now, but
What does that mean, shelf life of the tire after it's together? You know these trials you ran through, I can see them things just spitting through the process, okay? Bam, bam, bam.
that's right.
That's not everyday life in a plant. Okay?
The material we built with was 30 days old from the time it was calendared.
I'm talking about how long it hangs in a rack.
How long does it hang on a pin rack?
We looked at that as well, and there was no problem, at least with several days of it. On a trial we did in Albany.
Okay, but, you know, that's significant, because we get them together sometimes, right now. If they're stored too long under certain ambient temperatures, they fall apart. They're starting to fall apart.
The things that tend to fall off was when we were radiating treads. You stiffen up the treads and they tend to flap loose at the shoulders. The treads are a problem that way.
Yeah.
But in the body ply, there didn't seem to be any problem.
Of course, there's things we can do to help that, but I'm just talking about the way it is, not the way it's specified.
Some future programs from compounding standpoint, of course, one is to evaluate new, different types of resins to obtain our required tack level that we've got to have. And of course, the situation will be different for the different plants involved and the compounds involved. Number two, a possible cure reduction, as indicated by the rheometer data. We're going to point out that the body ply is not the minimum point of cure. Depending on the design and type tire, it's either in the shoulder or else in the bead area. So just something to think about as a far out program as a possible cure reduction, as Chuck mentioned earlier.
And one thing that does need to be considered when you're dealing with that item 1, if you're going to make again, from a calendaring standpoint, you're going to have the compound at the calendaring site tackier to allow you to have more tack after the pre-curing. then you could conceivably get us into a bad ballgame. We've
At the
already
calendar.
got, that's right, we've already got skims that are super tacky and subject to wrap up.
And just a question on the cure reduction. Since the point of minimum cure is going to be the bead or the shoulder, in what way are you considering by lowering the standard practice specification for cure at blowdown? I don't quite understand in what way you're looking at reducing
The remarks I made there is just based on the R10, R50, and R90 values seen from the regular production to the pre-cured material that we stripped off the calendar fabric. So I say it's a far out program. Chuck mentioned it also, a possible cure reduction. But again, we're starting out pre-curing the body ply, which is not the minimum point. When we get into some of the other programs of pre-curing the tread or SPI or the abrasion and down the bead filler, perhaps it'll become a more realistic item at that time.
Yeah, but doesn't the cure reduction result as a function of cutting down component mass, the gauges and so forth?
And we'll have to look at the whole thing as we get closer to that. But right now it's far out and it's possible. But I'd like to review the interliner penetration grading that we're using in analyzing the tires that we cut. The first is what we call an A-level penetration. There's no penetration of the interliner whatsoever. The interliner is not touching the cords. The interliner is straight across. We move to an item that we call a B-level penetration. The interliner stock, again, is not past 50% of the core diameter. And again, the interliner is not touching any of the cords. And we can break the B-level down into B1, B2, B3, depending on the height of the flow, as seen by the blue, green, and red lines. When we talk about C-level penetration, we're talking about the interliner stock flowing past 50% of the core diameter. If we say something has D-level penetration, we mean that the interliner stock is touching the cord. Now that could be touching at the bottom of the cord or flowing up around touching the top of the cord. In either case, we would call it D-level penetration. A regular production tire with non-pre-cured body plies and an insert between the interliner and the body ply at Wilson currently has A-level penetration. If we take out the insert and leave the body ply non-pre-cured, we end up with C and D-level penetration. If we leave the insert out and pre-cure the body plies, we move back into a B1, B2 penetration level. And I'll go through and show some photos of this here explaining that. First tire we built was a P195-14 WR12. It's a Wilson, February of '84, regular production control tire. CY157 body ply skim with an insert between the interliner and the body ply. The first photo is of the black sidewall shoulder, and I've drawn a dashed blue line in here to show the interliner and interface with the body ply. We see that there's A-level penetration and there's no interliner contact with any of the cords. If we look at the white sidewall shoulder, we see the same thing, A-level. I drew in the two cords here, it didn't show up. If anybody wants to look at the original photos, which show up much better the compounds, I'll have them available. But again, we had A-level penetration on the white sidewall side. As we moved into the experimental tires, we had pre-cured body ply skim with no insert. And we look at the black shoulder, pre-cured, or black sidewall shoulder, and we pulled this cord at the splice. Now in these tires, since the unit at Toronto could only handle, what was max width Al?
36 inches.
36 inches. We had to cut the fabric. So in many cases we ended up with 2 assembler splices plus a builder splice in each of these tires. And we pulled each of the assembler splices and the builder splice. The builder did this at the building machine. This is what we mean by a pulled cord at the splice. And you can see that the inner liner does not come in contact with any of the cords. There would have been a cord in approximately this area right here if we had left it in there. And we look at the black sidewall shoulder with the splice cord not pulled. We did not pull the splice. We see that it comes very close here, but again, the inner liner does not touch the cord. In previous builds, we have seen that this was not the case. When we did not pull the cord, we had inner liner contact with that cord. But here, it did not. And away from the splice,